Good day to all of you. Myself Dr. Arvind Sharma, Associate Professor in Physics, Government Nagar College, BIKANER. We are continuing our topic radar range equation, in which we already included many terms in radar range equation. Now the term we want to explain or understand about the noise power spectral density. What is noise power spectral density? Eventually we want to characterize noise. What we want? We want to characterize the noise in terms of power, in terms of its power at some point in the receiver. Noise in terms of power. However, to derive this power and provide a means of characterizing the effects of the receiver electronics, we will use approach commonly used in radar and communication theory. With this approach, we start by assuming that the noise in the radar, before we need to represent it as power, is white. Because of this, we start by characterizing the noise in terms of power spectral density. We start noise in terms of power spectral density or energy, which are the same in context. We cannot use power because white noise has infinite power. We cannot use power because white noise has infinite power. A very important point to be noted. Hence, we convert, that means we use noise in terms of power spectral density. We define the noise power spectral density in radar range equation by N0 equal to KT effective. Okay, where T effective, K is Boltzmann constant, T effective is effective noise temperature. Effective noise temperature, T effective. It turns out that T effective is not an actual temperature. Rather, it is temperature quantity that we use to compute the proper noise power spectral density in the radar. Okay. This point is also an important point, that this is temperature quantity that we use to compute the proper noise power spectral density in the radar. Although this may be confusing at present, it says that we need to know N0 to compute T effective, which we need to compute N0. It will hopefully become clearer when we understand a more detailed discussion of noise. Noise figure. As an alternate formulation, we also write T effective equal to Fn T0, where Fn in terms noise figure of the radar and T0 is a reference temperature, normally referred to as room temperature. In fact, T0 equal to 290 degree K, and we know that with the above we get N0 equal to KT0 Fn. N0 equal to KT0 Fn. It is interesting to note that which makes one that the value of T0 was chosen to be KT0 is a nice number and not because it is a room temperature. Effective noise bandwidth. Effective noise bandwidth, since N0 has the units of W per hertz, we need to multiply watt per hertz, we need to multiply it by a frequency in terms to convert it to a power. In fact, we use this idea to write the noise power in the radar as Pn equal to KT0 FNB, where we term B the effective noise bandwidth of the radar. We want to emphasize the term effective. In fact, B may not be actual bandwidth of any component of the radar. It turns out that if the radar transmits a single rectangular pulse, and if receiver employs a filter that is matched to the transmit pulse, and we are trying to represent the power at the output of this matched filter in terms of radar range equation, B is the bandwidth. What is B? Bandwidth of the matched filter. It will be left a homework problem to determine if B is 3 dB bandwidth. or the mesh filter, it will be noted that I placed a lot of caveats on our ability to tie V to a specific bandwidth. I did this to emphasize that we must be very careful in how we define the noise in radar. A very common mistake in the use of radar range equation is to use the transmit waveform bandwidth for B. For modern pulse compression radar, this is incorrect. If we combine equation 2.26 and 2.22, our signal to noise ratio PS upon N. PS upon N becomes SNR equal to PS upon Pn equal to PT ZT ZR lambda square sigma upon 4 pi whole cube R4 KT0 BFN L. What we have not done in equation 2.1 and equation 2.27 is state where in the radar we are characterizing the SNR. We will do this after we discuss some other topics. For now, we want to develop an alternate formulation for SNR which with one relation will take the same form. Okay, an energy approach for SNR. In this approach, signal to noise ratio, we define SNR as the ratio of signal energy to the noise energy, which you will recall the power spectral density. Recall that equation 2.22 is the signal power in terms in the radar. Again, won't say where yet. We further assume that the shape of the originally transmitted pulse is preserved. This means that at the point we measure the signal, it has a work peak power of PS for a duration of tau p, the pulse width, and 0 at all other times. This means that the energy in signal is ES equal to PS tau p. The energy in the noise in given equation En equal to N0 KT0 Fn. With this we determine signal to noise ratio SNR equal to ES upon En equal to PS tau p upon KT0 Fn equal to PT ZT ZR lambda square sigma upon 4 pi cube R4 KT0 Fn L tau p. We note that equation 2.27 and equation 2.30 are same if we let B equal to 1 upon tau p. In fact, equation 2.31 provides us with the definition of effective noise bandwidth as the reciprocal of the transmitted pulse width. Example, at this point it will be instructive we consider a couple of examples. For the example, we consider a monostatic radar and the parameters are given here. For the first example, we wish to compute SNR on a 6 dB SM target at a range of 60 km. To perform the computation, we need to find the parameters in radar range equation. Equation 2.27 and 2.30 and be sure that there are consistent units. Most of the parameters are in table 2.1 or can be derived from the parameters of table 2.1. The two remaining parameters are the target range and the target RCR, radar cross section, which are given above. The parameters that we will need to compute are the wavelength lambda and the total losses. If we use equation 2.27, which we also need to compute the effective noise bandwidth. The appropriate parameters are given in table 2.1, dB units and MKS units. Okay. If we substitute the MKS values from table 2.2 in equation 2.27, we just replace the values, then SNR signal to noise ratio equal to PT ZT ZR lambda square sigma upon 4 pi whole cube R4 KT0 BFN L, and it comes 27.41 or 14.38 dB. As a double check, we compute equation 2.27 using the dB values. This gives SNR equal to PT ZT plus ZR plus 2 lambda plus sigma minus 30 log 4 pi plus 4R plus KT0 plus B plus Fn plus L. What is SNR? PT plus ZT plus ZR plus 2 lambda plus sigma bracket minus bracket 30 log 4 pi plus 4R plus KT0 plus B plus Fn plus L, where all the quantities are in dB units. Where all quantities in dB units. From table 2.2 substituting yields SNR equal to 14.38 dB or 27.42 watt per watt, which agrees with the equation 2.32 except for the large digits of MKS values. Detection range. Detection range, one of the most important use of radar range equation in determining detection range or maximum range at which a target has a given probability of being detected by the radar. The criteria for detecting a radar is that SNR by the above some threshold value. If we consider the above radar range equations, we note that SNR varies inversely with the fourth power of range. This means that if the SNR is a certain value at a given value, it will greater than that values at shorter range. The upshot of this discussion is that we define detection range as the range at which we achieve a certain SNR. In order to find detection range, we need to solve the radar range equation R. Doing so by using equation 2.27 as the starting point, capital R equal to whole power 1 by 4 pt zt zr lambda square sigma upon 4 pi whole cube SNR kt0 bfn l meter. As an example of suppose we want the range at which SNR on a 6 dB SN. Target is 30 dB. Using table 2.2 values in equation 2.35 yields R equal to pt zt zr lambda square sigma upon 4 pi whole cube SNR kt0 bfn l whole power 4, and this comes 64957. That means 65, approximately 65 kilometer. We interpret this means that target will be detected at a maximum range of approximately 65 kilometer, or that target will be detected for all ranges of 65 kilometer or less. So we understand about the radar range equation in last 3 lectures. Okay, thanks to all of you.